is 7 o'clock, so we're going to welcome everybody. Welcome to tonight's forum. We tonight, we have a presentation by our very own Dean, KK4DAS. We're going to talk about the TinySA, which should be pretty interesting. So, Dean, do you want to kick us off here?
I do want to kick us off. How's that?
There you go. All right.
All right. Tonight's TNT forum is on the Tiny Spectrum Analyzer. I call it $10,000 in capability for less than $60, and I will show you why. So we're going to spend a few minutes and kind of go through what this device is, what it's used for, what it's good for. The TinySA, $10,000 in capability for less than $60. Really? Can it be true? Well, yeah, it can be true. So the TinySA is a spectrum analyzer. Until just a few years ago, the only people that had access to a device that could do what this thing could do were professional RF engineers that worked in professional labs, and these systems were very expensive. This is a Roden Schwartz. This is actually an inexpensive Roden Schwartz. They go up to $100,000 and more at very high frequency. They have lots and lots and lots of capabilities. Our TinySA, while, I made a provocative title for the presentation, is not actually exactly the same as that very high-end professional spectrum analyzer, but it's pretty darn good. And for our ham radio, amateur radio operators, it does virtually everything we need it to do. It does 100 kilohertz to 350 megahertz with pretty good precision, and it'll go up to 960 megahertz with reduced precision. So it'll handle all the ham bands that we need. It puts capabilities in our hands that we just didn't have available until just a few years ago. So again, it's not as precise or as capable as the professional high-end unit, but it's pretty darn good for the $60 that you got to pay for it. So what's a spectrum analyzer? Let's take a minute and talk about what a spectrum analyzer is. It's a signal analyzer that measures the magnitude of an input signal versus frequency within the full frequency range of an instrument. The primary use is to measure the power of the spectrum of known and unknown signals. So those of you that have kind of real modern SDR rigs that have waterfall displays, that's a version of a spectrum display. If you have SDRs, you can produce a spectrum display with that. But this is a dedicated instrument that lets you look at the entire spectrum at once, an entire range of the spectrum, and look at all the signals that are happening in that spectrum over a frequency range. So we talked about a couple of weeks ago a NanoVNA, and while these devices are virtually identical in their physical structure, they are very different devices. A NanoVNA is a vector network analyzer. The emphasis is on the word network. It's where networks of components come together. You use it to measure reflected and transmitted power, SWR of an antenna system, characterizing filters, things like that. So you see the NanoVNA up on top. The TinySA is a spectrum analyzer. It analyzes the entire spectrum and measures magnitude of input signals versus frequency. It's good for measuring component signals of a spectrum, harmonics, third order modulation, evaluating transmitter purity, looking for spurs, all of that sort of thing you can do with a spectrum analyzer. So it's a companion piece to the NanoVNA, but it is not the same, even though they look very much the same. And you can get confused if you're not clear. But they're very different instruments, and they have a very different purpose in life. The other thing you need to know is what's different between a spectrum analyzer and an oscilloscope. Well, an oscilloscope measures changes in voltage over time. And so you get that nice sine wave that is showing the peak-to-peak signal of a 9 megahertz sine wave over time. And the repeating sine waves are showing the repeating in time over some time domain. By comparison, look at the same signal on the spectrum analyzer. It's just a spike, just one signal, because the horizontal axis of a spectrum analyzer is frequency. The horizontal axis of the oscilloscope is time. So we are measuring amplitude of signals across a frequency spectrum as opposed to across a time spectrum. So that's the primary difference between an oscilloscope and a spectrum analyzer. We're going from the voltage domain, the time domain of voltage, to the frequency domain of voltage over frequency range. But they're both measuring amplitudes. They're just measuring it and displaying it in a very different way. Now, modern oscilloscopes like the Rigol on the left have a software capability called a fast Fourier transform, an FFT, that will produce a spectrum analyzer-like display, but it's a little bit lower fidelity and is not quite as good as having a dedicated spectrum analyzer. Same with your SDRs that you can buy. You can buy spectrum analyst software for the SDR, and they're pretty darn good and they work well. But I got to tell you, for $60, it's nice having a dedicated unit that you know is built for that specific purpose. What can you do? Well, you can measure all signals that are present in a spectrum. So this is an example I did just this afternoon. I hooked up a little antenna, and what you're seeing there is the FM broadcast band in the Washington metro area. So you got a channel on 99.5, you got another one on 91, and so on and so forth. So all of those are the FM broadcast signals, and that's just by plugging in this little cheapy little antenna that actually comes with the rig and just turning it on. And then just to show you some of the capabilities, it also has a waterfall display. So I turned on the waterfall display, and so you can see all of the signals in the FM band, in our area. And that's interesting, but what you should take away from this is it shows you all of the signals in a frequency spectrum. So if you have noise in your shack and you're not quite sure what it is or where it's coming from, you can use this to try and characterize what the noise is independent from the other signals. You can walk around your house with that little antenna on and see it change. I was able to see various devices that emit RF just walking around the house. So because it's showing you the entire spectrum, it's a very good device for doing that kind of testing and evaluation, looking for noise and that sort of thing. Here's another thing it's good for. If you look at this oscilloscope on the left, there's a square wave. And if you remember your basic theory, an ideal square wave should consist of only the components of odd integer harmonic frequencies. Well, how can you see from the oscilloscope what those odd integer harmonic frequencies are? And the answer is you really can't. But if you look at the NanoVNA, suddenly I can see the first, the third, the fifth, the seventh, the ninth, all those big tall spikes. Those are the odd harmonics of my input 9 megahertz signal. I got one at 9, I got one at 27, I got one at 42, I got one at 63. So you can see that right away I can now look behind that square wave and look at the component frequencies, the harmonic frequency, the harmonic series that make up that square wave. And that's just something you're not able to do with any of these other devices. It's a really good way to look inside the spectrum of a signal and see what is going on and kind of tear it apart and tease apart what's really happening there. So that's one of the keys to using. One of the things you can do with the NanoVNA is you can just analyze a signal that's, say, coming out of your rig and say, what is it doing? What am I seeing? Do I have weird things happening with it? Is it transmitting off frequencies? You can see all of that by pumping it into this pumping it into the spectrum analyzer. Here's another thing you can do with it. When we were building the simple single sideband transceiver, we used these ADE1 double balance mixers. That's the thing that's the little board that's up there on the left. And a double balance mixer, if you remember from your basic super heterodyne radio theory, takes in two frequencies, an RF frequency that's like coming in from your antenna, and a local oscillator that you're generating somewhere in your rig, and it produces a heterodyne signal at an intermediate frequency. So in the case of the simple SSB, our intermediate frequency is 9 megahertz. And so in order to produce a 9 megahertz signal from a 7 megahertz input, you need something that's going to add or subtract with that and equal 9 megahertz. So the 9 megahertz IF, we have a 7 megahertz input signal, RRF. So what do we set our LO to? Well, 16 megahertz. Well, what should happen in a mixer is the LO and the RF should mix. The 16 and the 7 should mix. And because it's a double balanced mixer, the only thing that you should see out of the output are the sum and the difference frequencies. Now, there may be some leakage of the LO and the RF, but if you're set up right and you put in the 16 and the 7, you should get 9 megahertz out, and then your IF works the way it's supposed to. Now, look at the oscilloscope trace. What a hash that is. How would you ever figure out what those frequencies are from looking at that trace? Because you've got two frequencies superimposed right up on top of each other, and it's just a mess trying to understand what that is. Now look at the spectrum analyzer. You got one peak at 9 megahertz, and you got another peak at 23 megahertz. Well, look at that. 16 plus 7 is 23. 16 minus 7 is 9. That gets you to your 9 megahertz IF. And then in a superhet receiver, that signal, those two signals would then go to a filter that would just dump out the 23 megahertz that is irrelevant. And so all you'd have left going into your IF amplifiers is just that one signal that's in the range that you want. And then you can amplify it, do all the things you do at the intermediate frequency. And then at the other end of the IF, you convert that to audio and then extract the audio from it and pull that out. So there's another real good example of what you can do with a spectrum analyzer. Anywhere you've got signals mixed up together, you look at the spectrum analyzer and you can see the constituent frequencies that make up that signal. And again, another good way to tease out where noise is coming from or what the noise is. You might hear it in the audio of your rig, but seeing it on a spectrum analyzer, you can say, okay, there's a frequency. Oh, is that 60 hertz power line noise? Is it something else? You can see what that signal looks like right on your spectrum analyzer. So that's kind of another thing you can do it. Another thing you can do with it is you can evaluate spectral purity. You can say, all right, how do I know that my rig is producing signals that are within the definition, the FCC Part 97 definition of spurious emission limits? So the FCC says that for HF, you got your spurs or transmitted spurious signals must be at least 43 dB below the mean power of the fundamental emission. So you can measure that by looking at the output of the signal of the TinySA, and you can see are your spurs at least 43 dB below the mean power. For HF, for VHF and UHF, if it's more than 25 watts, you got to be 60 dB below the mean power of the fundamental. And if you're less than 25 watts, it's got to be 40 dB below the mean power of the fundamental. So those are the rules. And if your transmitter is transmitting spurious signals that are greater than that than those offsets, then you're causing noise on the band. You're basically causing interference, and you're outside of compliance. Now, there are rules about transceivers, transmitters made before certain dates, and their grandfather clause and all that. But for any modern equipment, those are the rules. And so it's good to know whether or not your equipment meets the spectral purity specifications of the FCC, because we're all amateur radio operators. We're supposed to understand the theory and the rules behind this. We had the talk about safety last week. Well, this is just another form of it. This is about having a clean signal when you transmit, and so we'll talk a little bit. I'm going to talk a little bit about kind of what that looks like. First thing I'm going to show you is the rig we built, the simple SSB. So this is our Makers Group homebrew transceiver, and there's two pictures up there, and I did this for a couple of reasons. The one on the right is what it actually looks like when you're transmitting. So you got a nice, clean fundamental and virtually no spurs at the harmonics or anywhere else. Everything is well below you're only at 5 watts, but everything is well below the the offset that is required. And that's good. That's where you want it to be. Now, to demonstrate what happens if you're not in compliant, I just took the low-pass filter out. And the low-pass filter is the last thing that your signal sees before it hits the antenna. And you on the left, you see what happens when there's no low-pass filter. All of those spurs are just popping in there, and some of them are going to push us outside of the compliance range. So that's why, one, it's important to have a low-pass filter at the output, particularly if you're running power, because if I were taking that 5-watt signal and then further amplifying it to say 100 watts, well, all of those spurs are going to get amplified as well. So you're going to be creating a hash of the spectrum if you amplify that signal and transmit it out. So that's why it's important to kind of understand the characteristics of your equipment. Now, your commercial equipment should have been tested, but when you're buying used equipment, you're not really sure what you're getting. You've got old equipment that you're trying to rehabilitate, even though you're grandfathered with transmitters that were manufactured before a certain date. It's still just good hygiene and good ham radio behavior to make sure that your rig is compliant with spurious transmission specifications. So what about that $25 HT that so many of us have? How should we feel about that? Here it is on 70 centimeters. Looks pretty good. There's the fundamental there. That's the big spike. The second spike, number 2, is down 49 dB. So that sounds pretty good. We're at 5 watts. We're less than 40 dB. So we should be nice. We should be happy. So on 70 centimeters, we have a rig that is a little noisy but compliant. It is within the specifications. But what about 2 meters? Well, that looks really good. There's your 2 meter, 162.4 megahertz. Looks very good. Looks like no spurs, no noise. But there's a problem here. And the problem is that the frequency range of the low frequency input of the TinySA only goes to 350 megahertz. So if I want the odd harmonic of 162 megahertz, that's outside of the measurement range of the low input channel of the spectrum analyzer. So in order to really see it, I have to now switch my signal over to the high input and switch over to the high input measurement and see what that looks like. Now, one thing I want to point out is that our signal here is at minus 14.5 dBm. Okay, so remember that. Just take a note, minus 14.5. All right, so here's what it looks like in the high input channel. That number 1 there is the third harmonic at 488 megahertz roughly, and you'll see that it's at minus 34 dBm. Well, that's only 20 dBm down from the minus 14 from the previous screen. And the fifth harmonic is just as bad. So this rig, this radio, this $25 HT is not compliant. It is putting hash and noise out in the RF spectrum. Now, if you've read the QST articles on these imported HTs, that won't come as a surprise to you, but it brings it home when you measure it and you can see it. So remember, there's that HT, and there's the rig I built for $150 in parts and some sweat and tears. Look at the right hand. Trace, and you see there's just no noise, very clean. And then there's this commercial rig that many hams are using. And yeah, it's inexpensive, but what it tells you is we really shouldn't be using this on 2 meters. We should be upgrading our HTs to something better. Now, I have to admit, it's the only HT I have right now. After running this test this afternoon, I am now convinced I got to upgrade to something. And there you can get Anytones and other Alincos for $100, so they're not that much more expensive. But the $25 HTs are just, I can't say that they're all that way, but I know my particular one is not compliant. It's not good. And that's what you can do with a tool like this, though, is you can actually look at what your the spectrum of what your radio is transmitting, and you can it'll help you understand what is going on, and then you can decide what you want to do with it. But wait, there's more. You can measure third order intermodulation. You can measure phase noise. You can measure signal to noise ratio, and a whole bunch of other measurements in this device. Oh yeah, and it's also a signal generator. So if you need a reference signal to test out, to inject into your receiver to see if it's working, or if you don't have a separate signal generator, you can generate a sine wave from 100 kilohertz to 350 megahertz, minus 76 dBm to minus 6 dBm, perfect for injecting into the antenna port of your radio. The harmonics are below minus 40 dB of the fundamental. You can get an AM, FM, or wide FM modulated signal. You can sweep over selective word. It's a great little signal generator. It's worth the $60 just for the signal generator. And then if you need to go into the VHF or UHF range, it doesn't generate a sine wave, but it generates a square wave up to 960 megahertz from minus 38 dBm to plus 13 dBm. And again, you can use FM and FM modulated and slow sweep across that. So it's kind of not marketed as a signal generator, but it has an equally powerful and very useful signal generator that I have been using as we've been going through our build of the simple SSB over the past several weeks. So it's a really neat little device, given that again, it wasn't even available to amateurs and hobbyists for any kind of reasonable money as recently as 4 or 5 years ago, and now these things are ubiquitous. The same kind of engineering crew that made the NanoVNA worked on this, different software guy, and it's a different hardware architecture underneath, even though it looks like the same physical device because it uses the same user interface as the NanoVNA. But as I said, it's a completely different device. With any of these, with the NanoVNA and with the TinySA, they've been released as an open source project. So the hardware specs are all available and the software is freely downloadable. And there are many, many, many people that make knockoffs and clones of them. So it is recommended that you buy from one of the authorized resellers that are listed on the TinySA site. And the US one of those is RNL Electronics. And if you go to the tinysa.org website, it'll give you the list of authorized resellers and let you know where you can purchase it. There's a pretty good YouTube introduction by a European ham called the TinySA Video Introduction, and he will actually walk you through each of the menus and show you what they do and kind of step you through how to make the different selections. And then again, as I said, where to buy. The authorized reseller is RNL Electronics, and you can find them on eBay, but RNL, Brendan just said he ordered his and they shipped it within an hour. Sometimes they're out of stock, but you can order it anyway, and it usually comes in within a couple of weeks. Same with the NanoVNA. RNL is the same place that has the NanoVNA. So that's the story. I mean, it's a little more of the technical specifications if you're interested. But I think for the price, the capabilities are really remarkable. The fact that you can analyze the performance of your rigs, you can look at how your filters are working. You can understand harmonics. You can understand what's behind that funky looking wave on your oscilloscope. I think it's a really, really cool little device, and particularly for those of us in the kind of maker and building and fixing community, it's kind of a must-have, and it's a useful device even if you don't do any of those things. Even if you just want to measure the spectral purity of your transmitter, or if you are if you need a signal generator and you don't have one, for $60 you get a whole lot of capability that you can put in your bag. By the way, it's no bigger than a pack of cards. I mean, they're very small, very lightweight, and just a terrific little device. So that is the story, and I'm sticking to it. And we got a minute or two for some questions.
Okay, Dean, I've got a couple.
Why am I not surprised?
Why? Yeah, sure not. First of all, the signal generator, I guess that's a separate port, right? That's not the two inputs.
No, same port. Works on the same ports, yeah. So on the menu, you go to mode, and you can select low input, high input, low output, high output.
Okay, so you can't use it as a tracking generator.
You cannot use it as a tracking generator.
Okay.
Correct.
And the other thing is, what's the minimum resolution bandwidth on it? Do you know?
We'll have to go look at it.
Have to check the specs.
I don't remember.
Well, 0 to 100 dB of dynamic range is
2.16 kilohertz.
Well,
2.6.
Yes,
that's right. The resolution for switchable. Okay.
Yeah, so it has a there is resolution bandpass filter switchable for both ranges between 2.6 kilohertz and 640 kilohertz. So one of the things you need to know, I mean, when I show that first slide with the high-end spectrum analyzer, is it's got more capability. I mean, that definitely is more capable, but this one will do, like I said, pretty much anything we need it to do for our purposes.
Hey, Dean, I think it's an interesting point. Third from the bottom there, the fact that you can connect this to a PC like the NanoVNA, and so you get a bigger display and some.
Yeah, I don't like the PC software for it, so I didn't show it.
Yeah, no, it's not as good as the NanoVNA. But the question I have is, can you explain what you did to measure when you were measuring the harmonics on your HT? How did you prevent overloading the front end of this thing? Because it's pretty sensitive, I think.
Yeah, so I bought a pack of attenuators off of Amazon, little 30 dB, 20 dB, 10 dB, and I put 50 dB of attenuation on it. And so that's another thing. If you're going to get one of these things, don't just plug your antenna output in and start transmitting into it, because you'll blow it up. So I wasn't really intending to do a tutorial here, but it has a very sensitive front end, and you will blow it up if you put too much power into it. So read the TinySA.org webpage, and it describes everything you need to do. But I basically, if I'm going to put an input signal into it, I always have a 30 dB external attenuator on it to begin with, and usually I add more unless I am absolutely controlling the input. So like for the tests I was showing you today, I was controlling the input, and I still put an attenuator on there just to make sure that I was not overdriving it, because these are pretty easy to blow up if you put too much power into them.
And by the way, most all of your commercial analyzers by default have attenuators in.
It has an attenuator in it as well, but it's not enough.
Okay, that you can override sometimes.
Yeah.
So the 100 dB of dynamic range is rather interesting. I wonder how much of the processing is really done with an FFT versus analog.
Well, I'm not sure.
Okay.
I haven't done the engineering teardown of it. Others have, though. Well, cool.
I would imagine that it's probably not an FFT, and that it's just a tracking generator and then the resolution bandwidth filter following behind it, and power measurement to be able to scan that fast over those wide ranges with that dynamic range.
Yeah, it's certainly faster than the FFT on my oscilloscope. That is for sure.
Yeah, but to get the dynamic range they're doing is pretty incredible, I think.
Did we have one last question? I think we can take one last question.
Yes, I just wanted to ask Tiny, how tiny is Tiny? What's the actual screen size?
Oh, it's the size of a pack of cards, Rudy. I mean, it's You know, smaller than your cell phone.
Oh, okay.
Yeah.
Good. Thank you.
And it weighs about 4 ounces. So
2.8 inches. There's
I
Brennan.
carry that.
Yeah, 2.8 inches. All right. Well, thank you, Dean. Excellent presentation.
sure.
It was nice to hear about the little devices that are out there and on the market right now. So we have a lot. It's kind of a great time for amateurs with all these interesting little devices that are finally coming to market at more accessible prices. So it's cool to see another one out there. So.